SwayamPrabha. Digital India. Educated India.
Welcome back, and let's continue the discussion on the Reynolds stress model. And we looked at the complete equation, and there are different terms, and we will make some comments on those different terms and then look at the other analysis. So, this is what we looked at it. This is the total component of the Reynolds stress term, this is the material derivative, then it has production, dissipation and all these things. Some comments. One of the important is that for production term there is no closure required, then microstructure they are except close to the wall they are isotropic. So, that will approximate like this. Then also microstructure level negligible contribution to the shear stress. So, viscous dissipation rate of Reynolds shear stress neglected. Now, these are some of these things, but there are certain other problems like turbulent transport. So, this is one of the term which can create problem for the closure problem. So, these are closure problem. Turbulent transport is one term, then pressure strain term which is essentially responsible for return to isotropy or rather destruction of Reynolds shear stress. Now, in this particular set of equation this is computationally expensive because you have it is total 11 equation, 3 from momentum, 6 equation from the Reynolds stress and 1 equation from the viscous dissipation, then you have the. Now, important thing is that one can use this Reynolds stress model when turbulence is strongly non-local. For example, if you have a strong swelling flow or recirculating flow in presence of the mean flow. So, in those cases this RSA model is superior to all these two equations model and all these things. Now, that is a RANS based situation. Now, one can also have DNS, that means you solve all these problem where your averaged equation look like this, di by dt plus uj del xj 1 by rho del p by del xi plus nu del 2 ui by del xj square del ui by uj prime by del xj. So, this is closure was used, this is in the RANS context. So, closure used for the Reynolds stress. Now, in direct numerical simulation, so here actually you solve for the mean flow. So, that means if you look at the energy spectrum, there is a huge energy spectrum where if you look at kinetic energy energy spectrum. So, this is my LEI energy containing range, inertial sub range, and this will be dissipation range LDI. So, RANS actually solves for all the spectrum, this is what RANS does, that means the mean flow. So, it models the complete spectrum. Now, actual turbulence you have large scale structure, then energy transfer at the intermediate scale, then the small scale. This is where direct numerical simulation becomes important, which actually solves for each scale. That means DNS is instead of modeling it solves. So, here the equation system will look like, now you have the Gaussian equation and that is what it solves for without any closure. So, that is xi plus nu del 2 ui by del xj2. So, these are the equations which are solved for DNS. That means, the governing equations are completely, so no closures, essentially no closures. Now, that is a picture of how DNS looks like. So, this is taken from a channel flow simulations, where you can see the small scale structures are also captured. So, what you can note here, DNS can give you the complete description, but it is quite expensive. Now, if you consider an isotropic turbulence, that is again a specific case with a size L and velocity scale is like this, then all length scale of turbulence are to be solved. Now, energy containing large scale to Combustion scale in the dissipation range, so which will get you that delta x is order of eta, and your number of grid cells required would be L by eta to the power cube. And for the stability, one can look at the numerical stability point of view, which will be time step is required delta t order of delta x by u. So, that is you require, and the number of time steps required, that would be like k by epsilon by delta t, which is L by eta. So, the total scale cost scale width, essentially if you look at the total cost, the scale with NR time steps into NR grid cells, which is L by eta to the power 4 u L by nu to the power cube. So, that is why there is a limitation, serious limitation for low Reynolds number application, but these days, even today, the architecture or computational architecture is available. People can do large scale DNS. So, this is taken from the Pope. So, you can see for different RE lambda. So, this is an example for isotropic turbulence, different RE lambda and REL, what is the computational time required and like this. But as I said, with the advancement of the computer architecture and advancement of the available processor, now people can actually look at the large Reynolds number DNS kind of calculation. Now, we can estimate the computational cost for an isotropic turbulence, like you have this situation where dissipation range would be at this. So, then Fourier series of the velocity vector can be expressed like that. So, we can find out the large wave number in each direction, that will be pi by delta x, which is order of pi by eta. Now, smallest wave number, that would be 2 pi by L, and it is a majority of the modes in dissipation range. So, small fraction of that is in the energy containing range. So, that is what give you an idea what DNS is all about, and DNS requirement of the DNS for large scale, large Reynolds number application. Now, one hand you had, so this is an intermediate solution between RANS and DNS, because this DNS you resolve for all the scales, RANS you model for all the scales. In LES, what you do, you model for large scale structure, resolve for large scale structure, and only model the small scale structure. So, essentially theoretically LES can go towards DNS if your modeling part. So, there are two parts, one is the resolve part, another is the model part. Now, if the model part goes to 0, so this LES system should replicate the DNS behavior. Now, the large scale structure or the macro structure, these are most energetic structure, they will only contribute to mixing, and also they are anisotropic in nature. Whether if you look at the small scale or the microstructure, they are not energetic. So, they do little contribution to mixing and more or less isotropic or universal structure. So, the whole idea is that in LES you solve for this large scale structure and models for part of the model scale structure. So, as the small scale structure are universal in nature, so that is why LES actually this decompose into two components, one is resolved component and the model component. So, this is the modeling of the small scale structure and this is the result of the mostly large scale and the energy containing structure. So, this is done through some spatial filtering. So, there is a different kind of filters which are available. One can see there is a box filter, then originally the signal looks like this, then if you put the filter then it comes like that. Reconstruction obviously not exact, but it depends on filter type and the length which has been used. Now, this is an decomposition for LES, again it is an spatial decomposition, and where my UI would be UI plus UI prime. So, UI is GRX dot UI x minus RT dr, which is G into UI. Natural choice filter width on order of computational grid size. So, our LES equations become del UI by del xi equals to 0, del UI by del t plus del UI uj del xj 1 by rho del p by. So, this is a filtered component and this is the fluctuating component, rather after spacious filtering this is mean and this is fluctuating component. This is xi plus nu del 2 ui by del xj 2, and then we get a component from del ui uj minus ui uj by del x j. Here this particular term, this ui uj minus ui and uj, this is known as subgrid scale stress. From this comes from the small scale turbulent motion. So, only if you look at the equation system, this is continuity momentum, this is the term which remain actually unclosed. So, the closure problem is required for this, and this was proposed by a very popular model by the Smagorinsky, which is initially developed in 1963, and then later on this was modified by different people, and so this will give you an idea about when you use LES in multi-phase reacting system. So this kind of combustion going on where it is a real stick gas turbine combustion, where your liquid fuel is injected here, air comes through swelling condition, and this is the unsteadiness what one can capture. So now we go to the last part of the discussion is the correlation and some spectra, before we talk little bit more about the modeling aspect and all these things. So this is an image of a DNS calculation for channel flow, where this is the Reynolds number and this is the turbulent RE tau. So this is fully developed channel flow. So this will be statistically stationary and also statistically homogeneous in both x and g direction. So the Reynolds average can be based on combination of the ensemble average and linear line average like this, where Lx is span-wise length, Lz is a stream-wise length, Lz span-wise length, alpha is the sample number. So the requirement for the ensemble averaging, if they are uncorrelated samples, then the time interval between the consecutive scale, which should be higher than the order of L naught by U naught, or statistical convergence to reach for U prime. So the sample size could be quite large. So essentially when you do this kind of sampling, you need to, then one can find out 2.1 time autocovariance for statistically homogeneous turbulence are 1 R, which is ui prime at x, u1, this is u1 prime and u1 prime at r by x. Now if you normalize with a value at r0, then it will get you is u1 prime at x plus r, this is average divided by u1 prime square. So the properties that rho 11 at 0 is 1, rho 11 is rho 11 minus r, this is symmetric, then rho 11 r, the magnitude should be less than 1, and this tends to 0 for r tends to infinity. So that is a 2.1 time autocovariance for statistically homogeneous turbulence. Now again, if you look at the same calculation of the channel flow, you can see if you plot this normalized variable, this is how it actually vary, and from here one can define the integral length scale. The integral length scale would be the integration of r dr. So this is a characteristics for macro structure of turbulence, where you get an estimate of your integral length scale. Now we can define another micro scale which is called Taylor micro scale, which is lambda 11. Now our rho 11 r is 1 minus half r by lambda 11 r square plus some term, extra term for r by lambda 11 less than 1, where 1 by lambda 11 square minus del r square at r equals to 0. So we can estimate the viscous dissipation rate, which will be nu del ui prime by del xj square. Now for isotropic turbulence, it is shown that for isotropic turbulence, it is shown by Pope that 15 nu u prime by del x square. Now since dissipation occurs mostly at the small scale, so they remain highly isotropic, which is as per Kolmogorov hypothesis. So, this is also valid for other turbulent flow as long as RE is quite high, that means it is in the turbulent zone. Now, we can take the second order derivative of 2-point autocovariance. So, what that gives me, del 2 u prime x plus r by del r2 equals to u prime x del 2 u prime x plus r by del r square equals to u prime x del 2 u prime x plus r by del x2. So, now at r equals to 0, my this term would becomes u prime square del 2 rho 1 1 by del r square. So, this is u prime del 2 u prime by del x2 equals to half of. So, this is what that will give me, del 2 u prime square by del x2 minus del u prime by del x square, which one can approximate as del u prime by del x square. So, which follows that dissipation is approximated as minus 15 nu u prime square del 2 rho 1 1 by del r 2 at r 0, 15 nu u prime square by lambda 1 1 square. So, this is actually, this approximation becomes exact for isotropic turbulence. So, this is what one can get. Now, when you look at the 2-point correlation, so this provides the information about macrostructure for large L, which is the integral length scale, and then microstructure at small r, which is like this. So, if you plot this thing, this is what it varies. This is again for that channel flow that we have. This is an, I mean, one can do this for. Now, if you have a statistically homogeneous turbulence, so we can look at the Fourier transform pair of the velocity fluctuation u prime, which is u k equals to 1 by 2 pi minus infinity minus I k x dx, and u prime x is u k I k x dx. Now, this once we multiply this Fourier transform with a complex conjugate and use that flow for statistical homogeneous turbulence, what we get actually u prime star is essentially limit L tends to infinity 1 by 2 pi square x2 minus L2 plus L r equals to minus L x2 plus L x2 r 1 1 r e to the power minus I k r dr dx2, where r is x1 minus x2. So, we can use that r11 is symmetric and this can vanishes. So, our limit actually becomes, when L tends to infinity, this pi u hat by L become limit L tends to infinity 1 by 2 pi minus 2L to 2L r 1 1 r e to the power minus I k r dr. So, that is what one can get. And finally, this is our essentially, this guy is nothing but the E 1 1 by 2. Now, with the inverse Fourier transform, what we get, half k minus infinity to plus infinity E 1 1 k e to the power I k r d k, which will get us back k0 to infinity u11 k cos kr dk. At r equals to 0, this would be k equals to 0 to infinity u11 k dk. So, this is an energy spectrum. E11 represents the distribution of energy over wave number space. So, now one dimensional energy spectrum is twice the Fourier transform of the 2-point autocovariance, and that one can plot it for this channel flow, and this will look like this. So, these are the estimate of that thing what we just derived. U prime square would be the, and delta k would be 2 pi by length. Now, similarly, you can have the longitudinal and the transverse variation. So, the longitudinal separation vector parallel to the direction of the velocity fluctuations, where r11 is defined like this, and when we go to transverse, this would be transverse which is perpendicular to the flow, and their variation are different. The longitudinal variations is like this, where the transverse one initially quite steep and then it decays. So, similarly, for that particular case one can plot and look at it. So, this if you combine thing here, so one case you have a statistically homogeneous turbulence, you can have statistically stationary turbulence. Your 2.1 time covariance is calculated like this, 1.2 time covariance is calculated like that, because this is statistically stationary turbulence. Then one dimensional energy spectra will get you back the u prime square, this is frequency spectra which will get you. Then we can estimate the integral length scale, which is the macro length scale of the macro structure, and this is the time scale which we will get, because this is, and then the Taylor's micro scale and Taylor micro time scale. So, this is what it is in space and this is what it is in time. So, in space and time, how we actually, now already we have the Taylor hypothesis, where you can have an AD size like that, where u bar is coming and this is of the large scale, then one can approximate the space time transformation. So, for low turbulent intensity, where u by u is less than 1, you can get du prime by dt equals to du prime by dt minus u prime du prime by dx, which is minus u bar du prime by dx. So, which is order of u square by L minus u bar u by L, u bar u by L minus u bar minus 1. So, in other words, one can think that AD quickly advected by mean flow. So, this is the measurement location where we look at, such that it does not have time to change. So, the implication is that measured time series is in fact a spatial series. So, the transformation time is to the space. So, 1 by u prime square del 2 rho 1 1 by del S2 will get you del 1 1 by del R2, and omega by u prime tends to k. So, we will stop here and finish this one in the next lecture and look at the modeling aspect. Thank you.